Okay, targeted learning, that's the name of the book that you have access to. Really, just think of it for now as a combination of machine learning and causal inference. It's you're learning from the data, but not just prediction. You're targeting the learning from the data for a particular quantity of interest. And you know, the main developments that have occurred that have made this a practical methodology is first of all, important developments in this kind of statistical theory, really originally pioneered by somebody named Jamie Robbins at Harvard, and more recently Mark Vanderlyn, who's one of my colleagues. Basically try to develop new estimators of things that didn't assume a linear model or a logistic regression model. How could they do things, learn something about a quantity that didn't rely on a particular functional form, like a regression where you just simply report the coefficient or the odds ratio if it's a logistic regression. This has been huge, and this is really changing still quite quickly, is the cloud computing platforms that are affordable for anybody in here, for actually submitting things that used to be only, you know, government scientists working at national labs would have anything close to the access that you all can have, either through Amazon or other services. You can have at your fingertips thousands of computers for, you know, not forever, that starts to get expensive, but for periods of time where you can implement things that used to take, you know, to the end of the universe, and it can get done now in a matter of hours. That's really still, as more people get into this, like Google's getting into it, and they have a new platform where they include a lot of their own learning techniques and have access to huge amounts of data, lots of spatial data. These things are just getting better and better. So that's another big development. So they are really, in a way, a person without a huge amount of sophistication can now start to implement these methods on their own data, where it really was a much more specialized things. You know, the goal of all this, as I said earlier, is to develop what I call machines, meaning it's just automated. You know, you really, given most of us when we're approaching a data set, we only really want to put in to tell the algorithm what we know. And we want the algorithm to do the rest that's based on some kind of gold standard. I want to get an estimate of this thing that's most reliable with the least variance, right? That's the goal. And so if there's theory exists, at least asymptotic theory, meaning theory that I can predict when sample sizes get relatively large what will happen, you can start to develop algorithms that don't rely on human input anymore. Now, you know, again, I'm not saying this is a good thing for society, but for statistics, it might be a good thing. And that this can be much more automated, and my expectations is that it will get much more automated over time, where you want as few arbitrary human decisions to go in, because that just introduces a lack of reliability. Also, the fact that, you know, when you get inference for a quantity, it's based on the experiment you did, and rarely is it assuming that you've looked at the data first, or you made a decision because you talked to someone in the hall that said, oh, use the squared age, that fits better. These kind of things result in introducing bias, and it also is not the experiment for which it gives you back a standard error, which is I picked the model a priori, I had no input, and I did it once, right? That's the only standard errors you get back. And if that's not true, then how not true it is dictates how erroneous either your estimates or standard errors can be. And it's not really going to be necessary to have that kind of back and forth when you can have techniques that are just more guaranteed and more robust, that won't make the kind of mistakes that they could do now. I mean, if I have big outliers and I fit a line, the whole thing could be driven by 2 points, right? That's a trivial example, and you know, I'm not going to talk about that, but if it have some method that somehow can objectively detect outliers in some way and ameliorate the factor, at least give you a warning, you want those kind of things. These are, you know, a lot of this stuff is implemented now through diagnostics, right? You go through, you do your regression, you look at the residuals, are they normal, is there outliers? All this stuff, or related stuff, could be automated. Also, we want to do it for not just prediction. That exists for prediction now. I mean, they're not doing by hand too many of the kind of algorithms that check your credit card record and get an alert when you don't buy something. Those are automated procedures that are matching you with other people that have similar credit card transactions in some way, and pointing out that yours is next one was unusual according to some measure of of outlier, essentially like outlier detections. And so those exist now for prediction and are used widely in the industry. But it can also be done for things like impact evaluation, comparative effectiveness research I work a lot in. Can I really give the relative cost benefit of a certain new procedure? Implement in an area, individualized treatment regimes, which is really the key to precision medicine. These are things now where you can build machines. Why we're target learning is both kind of a theory and a certain algorithm. It's also sort of a style of teaching in some ways. There's a certain, I rely on something called a roadmap here, which is like, how do we specify a statistical problem? What are the list of things that we go through to make sure when we're getting a solution, we can claim, at least relatively speaking, it's somewhat optimal compared to competing things. And the idea is that you do something different, I have a different algorithm if I'm trying to optimize something like an association than I would be for pure prediction. Now, this is also kind of, there's kind of two things going on in machine learning, particularly in our field. One of them is this kind of work, but another one is like trying to develop algorithms that do a lot of, that do look at the data, adjust the number of, let's say, covariates in them or whatever it is, and then report the results, and then you interpret the resulting coefficients. Oh, these are the important things. That's erroneous. I just have to say, a priori, based on perfectly well-justified theory, that that's not targeted for that, and therefore it's targeted for prediction, but you're going to interpret it as telling you something about the process, and always be aware when you do that, whether it's fitting a regression tree or you're fitting lasso, which is, dominates my field right now. Everyone's doing different versions of lasso, which is a kind of penalized regression. It's really like, think of it, if you don't know anything about it, it's like stepwise regression. Think of it that way. It's just takes a large set of things and reduces them down to a smaller set. They're targeted for a certain purpose. They're optimized to get the best job predicting. They're not optimized for explanation. And also, oftentimes, the variables they choose are highly unstable. If I change the data a little bit, they'll give you a different list. It's because that's not what they're optimized for. So interpreting them as telling you something about the process, always dangerous. And that targeted learning, really, the other aspect about it is you change what you estimate depending if I'm interested in this risk factor or that risk factor or prediction. All those have a different algorithm because they all have different criteria. They have different standards you're trying to optimize.
I have a question.
Sure, absolutely.
Can you explain what makes it semi-parametric? I'm not quite sure how.
Yeah, that's a good question. We'll go a little bit more as we get to.
We're gonna do it later.
It's okay, but it's fine to do it now. So there's parametric, which means I can define the whole distribution by a small set of parameters. The most familiar one maybe being A equals A plus B x plus E. E is normally distributed. Sigma squared, let's say, everything's IID. So independent errors, right? So that means I can define the entire distribution of Y, given X in this case, let's just assume we don't care about X, by that parameter and that parameter, the assumption of normality and that parameter. It's a 3-parameter family. It describes the whole relationship. So that's a parametric model. It means I can describe the distribution of the data, or at least a portion of the data I care about, by a finite set of numbers, essentially. If I have those 3 numbers, I've described the entire distribution. Semi-parametric says, oh, it's a bigger model. I can't describe it by just a finite set of numbers. Now, non-parametric is the far end. You go from parametric to semi-parametric to non-parametric. Non-parametric is no assumptions, right? So no assumptions meaning, if I want to know, for instance, I'm going to use this notation here. This is the mean expectation, or expectation. So it just says, think of it as the population average of this outcome, that variable, in a group, in this subgroup, right? That's just a condition. And I might say, well, if I assume nothing, then my true mean for y given x is not described by some relationship between x and y given by the a and b, but it's just, I just have a different number arbitrary for every little x, right? If x is 0, there's one mean. If x is 0.1, there's another mean. If x is 0.2, there's another mean, et cetera. And I'm not assuming any relationship between them. Usually, we can't estimate things in non-parametric models because we don't have enough data, right? You don't, for instance, if x is measured as age to the nearest second, there'll be no ties, right? So every value of y, the mean of y given the x's I observe will just be a single number. It'll be an average of one number. It's a terrible estimate. It breaks down. I just can't do it. So you can't even get started there is the problem. So you have to say, okay, I don't want to assume absolutely nothing, but I kind of want my assumptions to be vague, like smoothness. That would be one. To say, well, there's some relationship between x and y. I just know something about when I plot, I'll say EY. Given x is equal to x here, you know, it could be something like this. It's just that these changes from up to down can't be too sudden. It has to be smooth. So smoothness might be one. In semi-parametric model. Oh, God, I have to write that bigger. So smoothness is just one. It doesn't tell you exactly what it looks like. It just says it can't jump up and down too much. It can do that via more abstract kind of, by the way, I'm saving all this.
Okay.
Yeah, you'll have the whole thing available to you, but you're welcome to take pictures. I don't care, but. Generally, it practically doesn't affect how we implement it. It practically affects the theory because you can't develop a theory under non-parametric. It's called the curse of dimensionality, when there's just too many x's such that finding any ties where which you get an average of the y's for all those x's is impossible because there's just data set's not big enough or it's truly continuous x's. Then you can't develop things that work in a non-parametric model. You get no ties, right? And you have to be able to average to use the central limit theorem, right? So you can't average, I can't get inference. And therefore you'll be like, okay, well, it's not that big of a model, meaning it's not no assumptions. It's some assumptions, but they're usually pretty abstract, like there's things called Donsker class assumptions. These are functional, people who are really mathematical work in functional spaces and they say, okay, it can have some, it doesn't have to be perfectly smooth, but the smoothness has to have, the roughness has to have some constraints and things like this. They're typically not practical constraints, okay? They're not like, okay, we can't do that because we need something that has this level of smoothness. It's also something we don't typically check in practice. The kind of algorithms we use to fit the data will impose these levels of smoothness. They just don't. They don't just connect the dots. They actually do fit through the data at some level, even though it's not a line. So that's a problem. It's a very, semi-parametric covers a class of models which are defined by these really weird, hard to grasp constraints. And I mean, I think probably the most tangible one is things like the number of derivatives that you have for a certain curve, right? If it has at least 4 derivatives or something, it doesn't, at some point, it doesn't get super rough. Yeah, but it's a very good question with not a very satisfying answer. I'll just say it's not going to affect us here. We're not going to be, if we can fit things non-parametrically, we're done, right? If I have x as 2 levels, I have an x as I have x is equal to 0 and x is equal to 1, and I want the mean of y given x is equal to little x, that is the mean of y for each level of x, that's what this means here, and I get a sample size of 100, what do? I take the average when x is 0, and I take the average of x is 1. That's how I get my e-hats, my averages, my estimates. And in that case, I don't need to do anything. I need no theory, I need nothing. I know that it's unbiased because I'm making no assumptions, and therefore there's no sense of doing any more complicated algorithm. That is the original history of statistics back in the time of Fisher and others, where a lot of the things they were estimating were simply the average of the outcome in the treatment group and the average of the outcome in the non-treated group. And they didn't need to model things because you know, they have limited levels, and you can always take the average of the outcome under each of those levels. It's only when the x's get more complicated that we need either to have parametric assumptions or some more vague assumptions which don't really limit that much the functional form. So a good way to teach almost anything is to start non-parametric, because everyone can understand averages, and then show how you go from there to something that requires a model. If in fact you have the curse of dimensionality, meaning you can't take averages anymore. Curse of, oops. And lots of people work on addressing the curse of dimensionality. In fact, there was a big debate recently at the SER between my colleague and Jamie Robbins about how to address this problem. So, and I have a side that I think is the right side, but I won't say. You can probably guess. Okay, just a little bit about the background on what you're going to do today. In R. So again, you're going to be getting into R Studio, and we'll go over some of these things right here. You know, basically just reading in data, the kind of forms of data I mentioned. When you're getting to R, you don't just have a data set. You have as many data sets as you want, and other objects like matrices and arrays and functional objects and lists, and goes on and on. How to do simple summaries. You know, a huge part of learning how to do at least develop new methodology, of course, simulation. Much of what I'm teaching you today, we develop theory for that we can show it works in a theoretically infinite sample, which of course doesn't do anyone any good in practice because no one has an infinite sample. But finite sample theory, that is a theory that predicts what's going to happen in finite samples, smaller samples, is impossible for most of these things. You have to know too much about the data generating distribution to be able to say anything definitive. So what do people do? Simulations. They say, in theory, it's supposed to work this way. In practice, how does it work when I simulate? Right? That's what simulations are often for. When you look at papers that are developing methodology in this field. So it's an important thing to learn about. And then some standard analyses that include these things. And then starting to get to more fancier things. These are, you know, data adaptive regression. Or, you know, you can think of them as machine learning algorithms. Again, machine learning does just mean I'm not going in assuming A plus BX. I'm letting the data tell me what the best fit is to the data. And so it has to learn the model from the data. That's thus machine learning. It's an automated machine that's learning. Then we're going to talk about causal inference. As I said, you have to have things to estimate. If I have a box which is, you know, a thing which is this, here's my inputs, here's my box, I'm fine, and here's my predicted Y, predicted. Well, if that's all I need, then I'm done. I just need to know machine learning, how to do it optimally, how to tell it what it's going to do in the future. We'll talk about that, of course, but then you don't really need anything else. But if I want to estimate, for instance, the effect of, let's take one I've been working on. It was the effect of an intervention in a childhood study where you give hand washing stations. Okay, so we did this in Bangladesh. And I want to know what's the impact of giving hand washing stations yes versus no, but there's so many other factors, right? There's all kinds of socioeconomic factors, other things that can confound whether or not someone uses hand washing things like soap. And so I have this black box, so I fit the data, but how does that tell me the effect of one of the X's, just one, is a treatment of interest? Well, how do they use that black box to tell me the effect of hand washing? I have to define a different parameter because there's no beta anymore, really. If you were doing this in a standard way, you'd have your outcome, that's fixed. You'd have your hand washing, that'd be a variable. Then you have all these other variables, right, in there. All the things you think could confound the relationship that you want to adjust for. And you look at the coefficient on hand washing and say, oh, that's my estimated impact. But there is no regression here, it's a black box. So you have to have some other kind of parameter that isn't a coefficient. And we'll go into the types of things, parameters that you can come up with. I think of causal inference as a little bit of a game, you know? It's a game we play to come up with measures of association that don't rely on a parametric model. And it's useful to take the game very seriously, and sometimes it's really, I have confounders, I have a thing of interest, I have an outcome. All the complexities of identifying certain effects are not that important. So it just depends on the context of whether the causal inference part is terribly crucial to understanding what you're doing better. But for us, the main reason is I need to estimate something that is not specified by a model, like, and we'll learn about this, I may want to know, let's say this is in theory, I love this one. So this would be my causal effect, causal average treatment effect. That would be we're going to talk about these, so we won't get hung up now, but these are counterfactuals. They're like the mean of the outcome Y if everyone had hand washing in this population, and this is the outcome of Y if no one had hand washing. And what I like to know is the difference of those two. That really gives me the causal effect, right? If I could keep everything else equal and experimentally manipulate this population to have the exact population have this condition and then that condition, that's how we're going to empirically define causality, the difference in the means, let's say. I obviously don't have data on that because not everybody has both. And usually nothing's the same anyway. If I give them treatment here and then leave and then I come back and then they're under control, that's not everything is equal. They've gotten older, conditions in the village have changed, right? There's other conditions that are not really controlled. So I want to come up with a different estimand, which means it's a statistical parameter of just the data generating distribution, the things I actually do measure, that will equal this thing under assumptions. And you always have to require, there's no magic here. You have to say, here are a certain set of assumptions. Causal inference is about learning what those assumptions are and in some sense how to test them when they're testable. Oftentimes they're not testable. And how you can create now something where I can use the black box to estimate components of the data generating distribution that doesn't rely on it being a parametric model. I'll give you a little future taste. Under assumptions, it will look like this. A equals 1. And I'll explain this in a sec. Oops. Well, I just messed this thing up big time. Here we go. Still getting my iPad legs. And let's see, I have WA. So I have a data set where I have these confounders. They affect A. My treatment of interest, this is hand washing. Confounders. This could be like diarrhea is what we measure. Right? So what this thing will show in the tomorrow, when we talk about this, that I can represent this thing, which is a function of random variables I don't measure. I don't measure the counterfactuals for each person, into something that's just a function of components of the data generating distribution. Just the mean when you're 1 and you have a certain set of confounders, so I can in theory get that estimate by regression or machine learning. And I can also do that for 0. I take the difference, and that sort of gives me the treatment effect for each individual characterized by W, and then I average across all the people, right? So this is now an estimate that is no longer a function of things I don't measure, and under assumption equal to that, so it gives me something to estimate. If I looked at it for the first time, I'd say, well, what the hell is that thing, right? You want to know that this thing is telling you something about the underlying association. Even in its form, it's not terrible, right? It's giving you the difference in the mean for groups defined by W, if I'm treated or not, and if these are all the confounders, it means sort of implicitly, well, that's the true difference between them, because I've stratified by everything that could affect A, so I've eliminated any of the impacts of W that come through A on Y, and now I get that for each person, and I can just average across the people to get the average effect. So there's some intuition that it's a reasonable association, but still, we want this. I could just start here and justify this and not bother with the causal part, but that's not the way it's gone, and that's not the way you're going to convince anyone. You'd like to say, under a set of assumptions, this thing is equal to kind of effect I would get at if I could do an experiment. And that's what causal inference is really about. It's about what are the type of effects that I want to get if I could do anything to answer the policy or scientific question of interest. And causal inference is the process by which how you can identify them by another equation, another parameter of the actual data. So from here to here are assumptions. Oops. Lots of assumptions. It's a good process because it makes explicit what you're doing, right? It's not built into some implicit assumptions about model type or anything like that. You're explicitly saying, I measured all the confounders. There's nothing else that's related to Y and A in my data. That's one of the assumptions you'll have to make, for instance. 2, there has to be enough experimentation, which we'll talk about, because if there's strata, let's say W is socioeconomic status, that's it. And I know I have people that are high and low. Make it very simple. So in theory, I could just do things by averages because it only has 2 levels. If there are strata for which nobody had hand washing, I can't estimate this difference, right? So that's another, it implicitly shows, I need enough experimentation in my data to be able to actually look at the causal effect. And that's often not obvious when you do a regression. It doesn't tell you anything about that because it extrapolates. Regressions, that's what they're great. They'll go from a couple points here, and you draw a line. Well, they tell you what it is here and here. They're extrapolating, right, outside the data support. But that means I actually don't really know the relationship there. I don't have data there, and you want a procedure that tells you, oh, you can't be answering that question. You have to ask a different one because you don't have the experimentation. And that's another thing these methods do, is they make explicit these kind of assumptions. Okay, we'll talk about substitution estimators. That's really how I convert the black box into an estimate of something. If I looked at the previous kind of equation, it means I need a prediction when you're treated and a prediction when you're a control. I need a prediction function to do that. That means I have to fit something, a regression or machine learning, in order to do that. But once I do that, I can just substitute in estimates of those things in and kind of forward model. It's essentially like forward modeling. I'm taking a prediction model and treating it now like nature and predicting what would happen if I changed nature. And then I'll predict it in 2 different ways and take the difference, right? That's a classic substitution modeling approach where you explicitly use that regression equation or that machine learning equation you got to predict what would happen in the future under different conditions that you change. And that condition could be, I don't change anybody's baseline characteristics. I don't change socioeconomic status of anyone. I keep them as I observe them. I only change the thing that I'm interested in looking at the impact of, which is hand washing in that case. And so we'll talk about this. And then we'll talk about how do we actually do that but get inference, because that alone will not generate an estimator where I can get a confidence interval. And that's because there's nothing about theory that will tell me that my prediction will be asymptotically normally distributed. That is, I can use the central limit theorem to get my confidence intervals, etc. I have to use the averaging that we mentioned earlier in order for that central limit theory to click in. And TMLE in one way is a very clever way of getting a bias rejection step and getting you to get some inference. There are other ways. This is only one way, but there's things like inverse weight. People have heard of IPTW estimators. Well, it's another way of using a non-parametric or semi-parametric way to estimate these kinds of effects. There's also something called matching. One of those is propensity score matching. It's another way you might have heard of. So we're gonna kind of bump up against these two techniques as we go through the course because they're alternatives and they really are motivated in very similar ways as we're motivating targeted learning, TMLE. If I have time, I'll talk a little bit about the more big data aspects of this because as I said before, if you have big data sets and not very adequate computing, these things can be impractical, just take too long. Machine learning algorithms often try many different models, and we're going to learn ones that try many different algorithms. So if you have something that's too slow for each of these, it can take days to get a very simple analysis done. So you need to use the computing architecture that you have available, or at least know how to go about it. I don't know if we'll get to it, but if we do, I'll talk a little bit about computer architectures, and it really is essentially just talking about the fact that you can have more than one CPU or one computing node in your computer. Anybody who has laptops here, like a Mac, probably has 4, right? So you could at least use those 4 in many of these algorithms. So it's not, if it has to fit different learners, it doesn't have to wait for this one to be done to fit the next one. It can go across all 4. Fit random forest here, and normal regression here, and et cetera. So you're able to duplicate tasks across different CPUs. And the way you utilize those is to use parallel computing. That's just doing that, right? There's complicated versions of parallel computing that are not intuitive. I'm not talking about any of those. I don't know them all that well. Sometimes they're built into the packages you'll use. I'm talking about what are called embarrassingly parallel. That means if I'm fitting 5 different models that don't rely on each other, I shouldn't have to wait for one to be done to do the other. I just submit them all together. That's embarrassingly parallel. And if you have more nodes, you can submit it that way. And then some tools for scalable computing that are related to these. And then the other thing that we probably won't get to, but is an important topic in big data, is flexible data structures. Like, you can't store things in matrices if I have billions of observations. You have to, particularly if a lot of the columns are empty most of the time, you need a different structure in order just to save it somewhere and access it quickly. And so there's things like JSON and other forms of data which you're probably, if you're not working in this field, you're probably not familiar with. But it's just a lot of practicalities come into play when you have really large data sets. Because I mean, if you even just try to open them up can take 10 minutes, right? And then doing a summary of a variable can take 20 minutes. And it just starts breaking down as a functional, practical way of dealing with data. And there are more and more programs that are being able to use the computer architecture to do this well. Stata has a big data version, so even standard things like regression become very, very slow. If I have millions of observations, then they have very clever ways of distributing the computations across different nodes and doing them in the most efficient way possible. Part of that is this thing up here, but part of it is also data structures. And this becomes really important in electronic medical record data because it's all time stamped, right? It's not like you're measuring one person and everything about them at one time. You get, oh, the person came in and they had this done. And then they came this time this was done. And you really want a data structure that mimics the process by which it's collected. It doesn't have to create every column for everything you might have measured. And JSON's one way to do that. It's a completely flexible structure. You sort of tell it at each line what the variables are that you're going to record the values for. So it's, usually we think of the variable's fixed, but in this case, the variable in itself is an input. And so it says, okay, I'm measuring heart rate at this time, right? And then to analyze it, you have to create different structures, but at least for storage, it's much more practical. Okay, let's, I think I've gone on long enough for now. Let's just take a 10-minute break, and then we'll reconvene at 3, and then I'll just go through the roadmap quickly before you start your R package work. That. You know, in some ways I'm caricaturing traditional approaches. I mean, I don't mean to be disparaging about these. I use them all the time, you know, in my own work. I think they have a place. And because these more modern methods, as I said, don't have the mature software yet, you know, they're still valuable tools for prediction and explanation and statistics. But traditionally, people would fit, you know, a lot of traditional, some kind of parametric model, usually logistic if it's a binary outcome, linear if it's continuous, maybe Poisson if it's a count, survival analysis if it's a right-censored Cox regression. There's these kind of, that's not a pure parametric model, that's a I should say that's a different definition of semi-parametric. Semi-parametric models can be models that have a parametric part and a non-parametric part, okay? When I say semi-parametric, that's not really what I'm talking about, but that Cox is a semi-parametric model in the sense it has a parametric part. It has, you know, a beta 1x1 plus a beta 2x2, et cetera, coefficients and things, and it has this other part that it doesn't specify. And then you report the coefficients, right? You use the coefficients to explain the association of a risk factor or a treatment and a disease outcome or a health outcome. What are the problems with the approach? Why do we even bother with a course like this? Well, one, all models are wrong. Have you ever heard that famous statement by George Box? I really think that's done a big disservice to statistics, actually. All models are not wrong, only wrong models are wrong. Some are useful, but he doesn't say which ones, and we don't know which ones. And this approach is generally trying to overcome that. I mean, he's highlighting an important issue that, you know, if you're trying to do things under parametric models, you're always going to be wrong because they're always arbitrary at some level. You really like to estimate things under a true model, which just means I only have the assumptions I really can justify from first principles. The parameters is typically, so the coefficient, when I say target parameter, in this case, you really mean the coefficient. Is estimated as if the model is correct. I mean, you don't go in and talk about the projected odds ratio on a misspecified model. You say the odds ratio, right? In fact, you even sometimes say the relative risk, even though it's an odds ratio. You go one step further, but it's usually, that's the way it's interpreted. It's impossible sometimes to have an easy interpretation of these coefficients when the model's wrong. Sometimes it's not so bad. Sometimes I can say, well, the true slope, there is no true slope because it's not a line. It's like this thing here. But I could say I'm interested in the average of the slopes across all these little slopes, right? Every point on this curve has a different slope, different first derivative you can think of. And so a projection of a misspecified linear model on that still gets something reasonable. I can understand that. That's an easy projection. That just means it's the best fitting misspecified model, which could give me sort of the average increase in the y or an increase in x. But once I get into multivariate models or any more complicated models, that projection is no longer simple. You can write it out mathematically, but it doesn't really have any necessarily easy interpretation. It's often deleted. That's just wrong. Estimated. So, I mean, in practice, and this is true with me and anybody, since they're not automated procedures, we don't just fit one regression model often, right? If you're in a really, this is also big differences between fields. Some fields now really require a priori specification of what you're going to do. You have to say what you're going to do. People are moving towards this thing called Open Science Framework, OSF, which says you put in your analysis plan, you put in your data what you're going to do, and you have to do that. And there's even publications in some fields that are requiring pre-specification. At least that gets around this problem, but generally, you fit something, and you're like, oh, there's these outliers, and you change stuff, and it could be you're doing the right thing or not, but there's no inference developed for those kinds of experiments where part of the experiment is the user changing what's based on what the data looks like. So, and that's almost never accounted for in let's say, when I say variance, just think of standard error of a coefficient, for instance. That's not accounted for. The standard error that data they return back is a standard error if you pre-specify the model, right? It doesn't, if I do stepwise regression, so I'm even explicitly stating, I'm not sure what the model is. If I did, I wouldn't do stepwise. So I'm doing stepwise, it gives you back the standard error for the last model, assuming it's known. Sometimes that'll be okay. There's times where that, under certain conditions, that won't be wildly misleading. Sometimes it's completely erroneous. And so there's a lot of problems with how analysis is done by using these kinds of approaches, because the theory that's developed to give you back the inference does not match the experiment actually done. And of course, there's all kinds of terrible pressures in science for positive findings, right? It's hard to publish the null. And so there's more. I almost never have anybody, when I have collaborators, when I go to them and I say, okay, I didn't find anything between this. I rarely hear, well, did you check an interaction? They don't say check an interactions, but I say, huge finding, right? There's implicit pressure to look at the data more when at first look it's a little disappointing. Totally understandable, but particularly dangerous for inference. And of course, this leads to these are old criticisms now, that really started in the 90s about epidemiology and other related empirical fields as junk science. I mean, in many ways, epidemiology is somewhat ahead of others in this regard because it has things like clinical trials. It understands pre-specification and this kind of stuff. But one of the big issues is if you give 10 statisticians the same data set and ask the same question, and it's a relatively complicated question, right? You're not going to get 10 the same answers, right? You may get some that give you the same sort of final conclusions about the particular question, but they'll all be different. There's too much idiosyncratic approach to analysis right now, and just really a function of the historical contingency of the things I've mentioned before. So you have arbitrary methods used, and I'm as guilty as anyone. Oftentimes, designs are not optimized to answer the question. People go into studies and they're like, well, I could ask one question for this, $1 million, but then that's not going to be very many papers. I could ask this question and that question and that question, and then you get basically a complex study that's not designed for any particular question. That can also hurt these sort of inferences. I mean, this I think is issues a little bit apart from the class, but a lot of our work really does rely on pure empiricism. We're just looking at relationships in the data. We don't have theory that tells us, particularly functional forms of how they're related, right? So very empirically examined, but empirically examined under really a small set of possible relationships we're going to investigate because we just didn't traditionally have the capability of looking at more. And then, of course, you can get these fishing expeditions, and of course that happens. It's just inevitable. Long-term grants have lots of variables. They're looking at lots of different questions. I've seen it kind of balkanized, and this person's looking at group as stress, and the other group are looking at smoking. The smoking people can't use the stress variables because it make the stress people mad because it's their study, and it's a human endeavor, science, and it has all the pitfalls associated with that, and the virtues as well. I mean, one thing that I can't answer because this is unanswerable is a lot of things are not measured, right? So we're even in these, the techniques that we're going to talk about are not magic. If you're missing important variables, then that affect the relationship you're trying to measure, these techniques aren't going to save you. They may do a better job in some circumstances, but there's no magic. I've already mentioned this. Computers. I mean, computers are obviously a great convenience for doing these type of analyses. If I wanted to do a logistic regression, I don't know, maybe 40 years ago, you guys saw, what was the movie called about the NASA women scientists?
Hidden Figures?
Yeah, the Hidden Figures. Those are room full people that are some of them inverting matrices, right? If I had to do logistic regression, I need a team of people to sit down and invert a matrix, right? So that you couldn't say, oh, can I add that interaction now? Because that would be another 3 weeks of work among a lot of people, right? So you can think of the computers as replacing all that. And that happened in the movie, right? The IBM comes in at the end. And you don't have to rely so much on human calculators like it used to. So in some ways, that meant, boy, you had a lot of pressure to get everything right first. You had to really think carefully with your with the scientists or the researchers about what variables were important and what should be included in the model, because you couldn't go back and change things because of the manpower. Computers make it so, it's so easy to just shift that. I'm going to make that binary. No, let's keep it categorical. No, let's make it continuous. Let's have an interaction. Should the interaction be the binary one, or it just becomes way too flexible, and that you can get a lot of overfitting, right? You start finding patterns because you're fitting the data so much, and again, it's overfitting in just that the standard error is underestimated because it doesn't account for the variability that comes from looking at the data. And as I said earlier, some disciplines are quite good about this and have been historically good, and we're not the worst, so take pride in that. Also, I find this, I work a lot in genomics and high throughput geology, where you're collecting millions of variables on each person, millions of genes, SNPs, or millions of gene expressions, or protein expressions, or methylation, or microRNAs, it's a huge list of things you can measure. Incredible revolution in being able to measure tons of different biomarkers with one chip. But that also just opens up, that field's probably been, and it has been shown to be riddled with false positives. There's an interesting aside of that. That's beyond the fact of the usual thing of just trying too many things and just only reporting the things that work, which I don't think anyone doesn't. It's rare that's nefarious and they're really trying to find a finding, ignoring the science. But even when you get everything's pre-specified and you're testing making a million tests, it turns out that the central limit actually breaks down, even if I have a relatively large sample, in the tails, right? It tells you, the central limit theorem tells you that if I take an average, if I take an average of one number, so I'm just taking somebody's blood pressure, just one blood pressure, and that's going to be my average. And I redo that experiment with somebody else's blood pressure, and I graph that distribution, right? It's going to be, it's not going to be very normal. But if I take 100 people and average it, and then I take another 100 people and average it, and I graph those averages, it's going to start looking pretty normal, right? So this is n is 1, and this is n is 100. And then eventually, it'll look like that. That's what the central limit theorem tells you. That's what we use to get our p-values almost all the time. Well, it turns out, yeah, that works really well when you're maybe this part of the distribution, but for multiple testing, you have to be able to it has to be perfectly normal way out in the tails, and that takes huge sample sizes. So a typical sample size in a genomic experiment, really, it started out being a sample size of 2. One person, let's say, with cancer and one person without, and that's absurd. You can't do inference on anything, but people will get t-statistics. But actually to do something and say, and if you have a million things, it takes sample sizes in the billions to be confident. No one has them. It's a real chronic problem in this kind of data. And I think it's well recognized. So other issues come in that are even worse than the things I'm talking about.
And just to clarify, is that just because the data are so sparse there? Like if you're talking about a z-score on 3 or 4 or 1,000, you need millions just because there's so few events at the tail?
No, yeah, exactly. Exactly. It just means if I'm taking repeated, if you just do experiment on the computer, taking repeated averages of, let's say, a sample size of 100, and you're calculating what's the probability that a certain average will fall in the upper 5%, you can do that fine, assuming the normal. In the upper 0.00001%, you need huge sample sizes to estimate that tail perfectly, because if I am just a little off, a significant p-value goes to non-significant, and vice versa. And that's the problem. It's just basically, you need a big sample size, so it's not just normal on this part, it's normal way out here in the tails. Magnitude of this problem, who knows? I mean, people have done really interesting studies. Ioannidis at Stanford has done studies where he's gone back and looked at findings from prominent journals, including Nature and Medical Science, and then traced to see how many years later whether they held up, and the percentage that held up is unbelievably low. 5%, 3%, really, really low. Psychology has had interesting studies recently where they've just redone the analysis of the existing data, and they couldn't reproduce, more than about, I think it was about half of the top 100 studies in psychology. So it's just a chronic big problem in empirical fields right now. It's widely recognized, people are trying to address it some way by pre-specifying and having this sort of open science framework type of things, but still, it's an issue. Part of it has to do, not all of it, but with the kind of coming up with methods that don't have as much user interaction with the data, more automated. So what we want to do is just try to reduce the biases we can control, even if we can't reduce the biases we can't control that have to do with unmeasured things like that. But we can at least say, given what we have, can we get an estimate that at least respects the model in a way? And that's where machine learning comes in, because it doesn't assume much of anything. All right, just to go for a little really non-rigorous history of statistics, the one that sort of conveniently tells the story. Here's the Pearson chi-square test paper. So this is back in the day where you could collect objects under two different conditions, whether they're plants and how fast they're growing, or there's or whatever it happens to be, and you want to see whether or not this fertilizer changes production of plants in the field, or whether smoking is associated with lung cancer. Just two states, in this case, both of them binary. The intervention or the exposure is binary, and the outcome is binary. And in that case, you can simply use the essential limit theorem. You're not really making many assumptions. You can do it by hand. And given that's your world, you can really trust the results, right? That p-value means something because there's lots of justification for that chi-square statistic being chi-square distributed under the null. So you get correct p-values, and that's kind of the standard. And a lot of the science matched that kind of structure. So not a huge number of variables, didn't have those kind of data sets, couldn't be handled anyway. And sure, there's limitations, no doubt, because you couldn't measure things that were relevant, but at least for what you did measure, you could assume you got that part right. I'm going to use, this is an old, and I need another study, but we use a lot at Berkeley. It's very much similar to the Framingham study. It's recruited at work, and they followed them forward, and it was designed to look at personality type and heart disease. So whether if you're type A, stressed out, hard driving, versus type B, the mellow, surfer, is the, sort of the caricature, whether that had an impact on coronary heart disease. So they recruited this, it was back in the not so good old days, everybody was essentially all white men in this age group, and they followed for 10 years. Behavior type was the big big exposure they were interested in, so A versus B, stressed out versus mellow, to oversimplify. And then they looked at the outcome as binary, which was whether they had a heart attack, some kind of coronary heart disease event, around 3,000 subjects. So we'll use other data sets here, but it's one we'll use because it's simple, and it's a good place to start. I don't know much about this personality theory, and I think in some ways this has been, maybe not discredited, but certainly become more complex over time. But that's what they were testing. And this is what it looks like, right? This is good old Pearson chi-square test. You have a 2x2 table. I don't have to do any modeling, right? I can get the proportion of people that have a heart disease in that 8 years who are type B, and there was about 1,500 of those. And there was 1,500 or so of type A, and they had a rate of 11%. And of course, I can report that difference in different ways. I can take the difference, I can take the ratio, I can take the odds ratio. It's a question of what parameter you think is more meaningful, or you can estimate. And then I can assume that this thing, using the central limit theorem, that the null, if there was no association, I'd have it would be chi-squared distributed, the chi-square statistic, and I can compare that to the null distribution, and of course that's impossible, right? So all good. Like this is the kind of thing you always want to do this if you can. If there's no reason to go beyond this, you're not helping yourself by being more complicated. Because I can trust the theory and I can trust the inference. And then again, you have to define your parameter of interest, which we're gonna do. This is pretty straightforward. Using my notation, just to give you a little bit of, that's like probability y is equal to 1, given A is equal to 1, minus the probability y equals 1, given A is equal to 0, where this is ECHD and this is behavior type A, B. So I have, A causing Y, and so far I don't have a W, but it'll come in. I don't have other confounders. Just to note, because it becomes later, that the probability Y is equal to 1, the proportion of times Y is 1 among those that are type A or type B is the same as just the mean of Y, given A is 1. Right, so logistic regression is often thought as modeling probabilities. It just models means. It's just the mean of something that has two levels, and the mean of something that's either a 0 or a 1 is the same as the probability that is 1. It's just and if I just did, for instance, probability p hat y is equal to 1, that is the estimate for my data is just 1 over n yi. I equals 1 to n. So if I just sum up all the y's, that's the total number that had the event. I divide by n, that gives me the proportion. That's also an average, which is a mean, right? So I can write them either way. Of course, I can also make that a ratio instead of difference, or I could make it these other kind of parameters as well. Okay, so people realize that's great if I randomize behavior type, but because if I randomize it, as we'll learn in the next section tomorrow, then I can interpret that empirical difference in the means of the proportions as causal, right? Because nothing caused, there's no relationship between who got personality type and the outcome if I just flipped a coin, right? I didn't look at their disease state sometime in the future and use that to decide who is going to get type A and type B. It's just, it's not randomized, but if it was, then I can interpret that simple empirical difference as the causal impact of behavior type, right? That's why we do clinical trials. It's because we break that any relationship between factors that might have influenced it and the outcome by randomizing it. But if I didn't have that's the case, if it was an observational study, right, then I would have to account for those other factors. And the easiest way to do that was stratification. Let's say it was all about age, for instance, and you get more stressed out or more mellow as you get older, for instance. Then one way I could eliminate age from the equation is just say, well, I'll just fix age to be 50, and I'll look at the difference in the rate of heart disease and the proportion among those who are type A versus type B if you're 50. And I could do it if you're, therefore, age can't influence it because they're all the same age. I get rid of that confounding by stratification. And so they generalize the sort of methods by allowing for stratifying, not just having one 2x2 table, a behavior type versus coronary heart disease, but having a sequence of stratified tables where you're stratified on the factor that you think influences both behavior type and the outcome. And of course, the most, a famous example is the Mantel-Hansel test, right? How many people have heard of the Mantel or the Cochrane-Mantel-Hansel test or the Mantel-Hansel test? Okay. And then you can also say, well, I want an overall association, and if I believe it's the same for every group, I can average them. That's all Mantel-Hansel is. You just say, get that risk difference or get that risk ratio for each table and then average them in an appropriate way if you think they're the same. But now, since they're all unconfounded, they're not being influenced by extraneous factor now within each table, then the average of them is also unconfounded, and that's the idea. And again, I can do this by hand. I'm not making any modeling assumptions, right? I have to make the assumption I've got the right variable I'm stratifying on, but assume it's what I have in hand, then I can do everything without modeling. It's still non-parametric. And now this isn't this is what's used in the books where it's presented. Behavior type isn't the best confounder because this is body weight category because body weight you might think is downstream, not upstream, but ignore that for now. We'll just stratify. We'll just assume that we have W, which is body weight, going to A, which is behavior type, which is going to Y, which is coronary heart disease, and the possibility that W affects both. It affects your behavior type and it affects your coronary heart disease. You just get the difference. That's just that mean difference or that proportional difference within each group of the proportion of people that have disease. If type B minus type A, I get it for each strata, and then I average them. That's all it is. That's the Mantel-Hansel. Again, if we had data structures that look like that, there'd be no reason to do machine learning. You could just say, okay, if I want to know the association, I just find it in each group by just taking simple averages of things, and then I can leave them. I could just report each of these. That's one thing I could do. Or I could average them and get the Mantel-Hansel. But again, I'm not making big assumptions here, or any assumptions really. And here is where we get the problem. This is where regression came in. And here's an example of the curse of dimensionality. What I did here is a very superficial thing. Is they had about 6 confounders. I made all of them binary, and then you can make strata defined by all of them, like age and body weight and cholesterol they had blood pressure, they had all these other things. So I said, okay, high and low for every one. And then I just made strata. If you're high, that's one group. If you're high, low, high, that's another group, et cetera. Every group. And then you get the difference within each group. Perfectly fine, except what you start seeing is like there's groups that have no people in them, right? You start getting empty cells. And you also have strata which are small, 9 people, 3 people. And I'm getting a terrible estimate of this thing because I only have 3 people, right? And it's a binary outcome, so it means at least somebody had the disease, and one of those 3 people. But that's called the curse of dimensionality. It means when I'm stratifying by so many things, I just don't have enough data anymore to estimate within each strata, and the whole procedure breaks down. So what do people do then? If they can't do stratification because they have too many variables, And this assumes they're all binary. Now if they're continuous, it'd be even worse. If they were truly continuous confounders and I made strata, it'd be one person for each strata. I couldn't even get an estimate for any strata. So what's in this context, if I have a binary outcome, I have a binary variable of interest, and then I have a bunch of other variables, what do people do?
Just using a regression model.
Yeah, logistic regression, not regression, but logistic regression. You fit Y versus A and all the W's, and you fit it, and that has an analogous sort of interpretation to stratification. You're essentially like stratifying all the W's, but you allow that stratification to occur by a model. You allow that, well, the log odds in this case goes up linearly if I increase body weight, or it goes up linearly or down linearly if I increase something else. But you can no longer do stratification because it doesn't work anymore. You don't have enough data, right? And so this is logistic regression. This is a very non-scientific survey of PubMed looking at the number of people that use logistic regression in the abstract, going through these times. And you can see sometime here is where SAS on PC became available. And if I did this, it's just like, it's way up here now, right? So the explosion of use of regression. Because now I could collect all this data. So stratification methods are not available, but I don't need them anymore because I don't need to do them by hand. I can use a computer, and nothing stops me from just adding more stuff in my model, right, up to a point. And so this really took off as a way of addressing these kinds of problems. And of course, the issue is, of course, why logistic regression? I mean, it's just one arbitrary model of an infinite number of possibilities to investigate the association. So, but it's convenient. It makes sure that the prediction value falls between 0 and 1. It's the mean of a binary thing, which means it can't be less than 0, and it can't be greater than 1. So logistic regression guarantees it's in that range. That's useful. It has coefficients that you can interpret directly, right? I don't have to do a lot of work or use the model to predict under different regimes. I can just look at the coefficients. So it comes directly back from the fit. I've got my parameter I can report. Lots of convenience associated with it. A lot of reasons why it became very popular. Another big thing, of course, case control studies became very big in epidemiology because you could show that you may not be able to estimate the risk difference. Obviously, I can't. If I've controlled the number of cases and controls of my population, coronary heart disease, I can't look at the probability of coronary heart disease. I've set it at 50% or whatever it is, so that's not available. Relative risk, likewise, is not available, but the odds ratio, it turns out, has this weird mathematical property that it's symmetric. That I can look at the probability that you're type B, given you have coronary heart disease, and the probability that you're type B, given you don't have coronary heart disease, and I can make an odds ratio that way, and it turns out to be equal to the other one, which is just a mathematical quirk of the odds ratio. So I could run logistic regression and get back something that relates to the parameter I'm interested in, even though the data is biased sampling, where I can't get any information about actually the underlying rate of the disease directly from the data. So for a lot of those reasons, it really took off, right? Both case control studies, because you could study rare things. I could study rare cancers now because I don't have to prospectively get huge number of people for just a small number of cases. And you could use logistic regression. And again, that whole being able to interpret the odds ratio that you get back from logistic regression from using case control data really relies on the model being right, okay? And the projection of that thing on a misspecified model gets even more complicated. So it's even more problematic in some way. So you need something that can handle high dimensional data, lots of variables. Or some continuous. But doesn't have to rely on an arbitrary model. And therefore, I mentioned this earlier, we're going to go, all these things we're going to go over lots of detail one at a time in the remaining sections. So this is going to seem, I'm just trying to give you a reason why you took this course. I'm not trying, this is not the last we're going to visit this. But in this case, you need a different sort of parameter of interest, since I have a black box, I don't have a coefficient. I can't write down the model afterwards when I fit it now for a machine learning algorithm. So I need something, as I said earlier, it's going to look like this. I've used this a lot in studying transfusion ratios among acute trauma patients. This is the patient comes in, there's some debate about how many platelets to give and when to give them and what platelet ratios are optimal. You know, the history of blood transfusion used to be whole blood, right? And therefore, you just got whole blood. But then you can't do kind of industrial scale for that, so you had to spin off the components, the red blood cells, you know, the serum, the platelets, et cetera, the plasma. And then, of course, there's saline as well. So they try to they are now, just give red blood cells and add some saline, but that doesn't work very well because it's not the same as giving blood. And now they're trying to go back and say, how do you mimic, in some sense, something like whole blood when you're trying to get someone to stop bleeding, but you don't want them to clot too much, right? So how much platelets to give them? And we're taking these sort of observational studies and try to determine, what would be the rate of death if we gave everyone a certain level of ratios. And this plot just shows, there's accidents and things that happen. There's the treatment, and then whether or not we're looking at death as the outcome here, but other outcomes too, like the organ failure and other things. So again, traditionally, people would get data like this and maybe fit a linear model, and we're going to get away from this. That's an X. And try to fit things more like machine learning algorithms like this one that can actually fit this data. Since if we gave, and just that's a main thing, you need data adaptive methods. It's just we don't ever know enough to specify the model ahead of time. And so you need methods that will explore the data, but will do it in the right way. It's really easy to overfit data. If I have an algorithm, if I just do it by hand, if I have 100 covariates and a sample size of 200, I guarantee you I can fit that data perfectly almost if you give me enough time, right? But you want methods that don't do it in an ad hoc fashion, that somehow have a systematic way of choosing how to fit the data so they get the best job possible without overfitting. And we're going to talk about, that's machine learning, which we're going to talk about. And that's, this problem has been called the quiet scandal of overfitting models that occurs in empirical science. This is written by a guy named Leo Breiman, who was a big machine learning guy, one of the original ones. And much of his work was intended to address this problem. I'm going to skip this because we'll go over more detail later. So basically, what is statistics? It's the science of learning from data. That's what it is. That's the definition of statistics. You want to learn something about the data, and you want to pre-specify some question, or pre-specify at least some aspect of the data, even if not a particular parameter. And then you have all these components to come up eventually with the estimator, the algorithm that you're going to implement to actually get your results in the end, and both the estimate and the standard error. So one of the big steps, and one that we're not going to talk as much about here, is you have to be able to really characterize the experiment well. We often have pretty complicated experiments, like we might take people from clinics, right? We need it's rare, at least in the studies I've been involved with, that people go out and take a real random sample from the entire target population, right? Usually when you're making inferences, you want to say, here is something about all the people that could be at risk for a certain disease. I'm going to say something about them. And the best design, maybe not the most efficient, but one you don't have to worry about bias, is just have a random sample of that group, completely random, follow them forward. So I know I'm getting a sample that's characteristic of the group. It's not biased in any way. And I don't have any other things like I tend to collect people that tend to have similar results in groups. But that's almost not the case, ever the case. You know, we often sample by clinics, or we sample by days of the week, or whatever it happens to be. It introduces these other elements that have to be accounted for in the analysis itself. And there's a lot of classes that deal with that. You know, repeated measures classes, if you're taking replicates on subjects, survey sampling, if you have a bias sample, all kinds of aspects that deal with that. We'll talk a little bit about that in this course too, because it's important how you implement machine learning, that you do it correctly. You want to specify a statistical model that's true, right? You know you're going to do a better job if you're estimating things under a model that doesn't make arbitrary constraints. It's fine to make a model that's too big. In other words, you could have made a smaller model because maybe the truth is that everything is linear. It's okay if you don't assume it's linear. That doesn't hurt you. I mean, it can hurt your efficiency, but it doesn't hurt your bias. It could mean your variability is going to be higher than you want, but at least you're not going to enter bias. It's when you assume a smaller model and it's not true. That's where you're in trouble. So I assume it's linear or logistic, and in fact it's more complicated. Then you're adding bias. So you really like to specify what your statistical model is. What's the shape of the relationship, for instance, between the outcome and the predictors? As I said before, you can't solve every question with a single analysis. It has to target each question, so I have to specify what's my parameter. Is just the predictive value? Am I going to come up with a diagnostic routine where you put in the inputs and I'm just going to tell you something about the state of the patient in the next hour? That's a prediction problem, so my parameter of interest then is just the probability that they're going to have the outcome. Or is my parameter something to do with the impact of treatment? You have to specify what it is, and of course you want it to tie as closely as possible to the scientific question. Once you've done those two steps, then you want to choose an estimator that has some kind of optimal properties. You have to specify, well, what, usually this is based on specifying what's called a loss function. For instance, I may say, let's say, I'll just call theta is my truth. It could be a relative risk, a true relative risk or something. And theta hat is my estimate, right? I could say what I want is the difference between that and repeated experiments, maybe squared, is small as possible. Okay, and this thing, of course, is the mean squared error. Right, but you have to specify what it is. The estimator, you know, the way the methods will be developed based on methodologists and theoreticians will be, okay, here's your mathematical problem, here's your data, here's the thing you want to estimate. Can I come up with an algorithm which is guaranteed to be, at least in the limit, at least as sample size grows, to give you an answer that's as close to the truth as possible, that this distance here is small, right? So you have to specify what your objective is, and that leads to an estimator. Now you can have suboptimal estimators, but it, of course, is better to have ones that are optimal if possible. It's not always possible to specify what's going to be the best, but often cases it is possible to say that these kind of algorithms will do a better job than these kind, right? So again, this isn't a theory course, but the idea is we'll talk about techniques that competitors will expect it not to do as well, and we'll rather do something that gives us closer to the truth. To really understand all this, you need to know all these things. And some of these things I know, some of these things I have only a really pretty unsophisticated understanding of. So you can be a practitioner of this stuff, at least I think you can be, at any level. You don't often have to do lots of math for these things because the black box is doing it for you. But it's good to have some concept of what's behind it. So the three major things you need to learn, we're going to talk about causal inference. How do I create parameters that are interesting and I can justify their estimation for the question of interest? This is really machine learning. We're going to talk about super learning because it's an optimal machine learning, right? I talked about you can fit different algorithms. I want an algorithm that does the best job possible. Well, super learning is an algorithm that has the properties that it does as good as you can do, and then you need, finally, some way to convert that prediction into estimates of something that you derive here. All of these require knowledge of some things that can be very difficult. Empirical process theory, high-level mathematics, efficiency theory, developed only 20 years ago, also very complicated. We're going to talk a little bit about something called the influence curve, because that's how we get inference, it turns out. But again, I don't expect anybody in here probably to have much background in these things, and you don't need it. But we are going to study the estimators involved, and these are the things that are propping them up, right? These things have an underlying justification, and that's why we're doing them. One thing we are going to talk a lot about is cross-validation. When you're doing adaptive things, cross-validation becomes crucial because that's how you avoid overfitting. And much of the algorithm theory developed relies on cross-validation. That is, I have to have some way of knowing that this thing is going to work in a new data set, that it's not going to be overfit. So the way you do it is you split up your data in these clever ways, and the portion of the data you fit a bunch of algorithms, you make a linear regression, more fancy things, and then you try them out on the leftover portion. And I know that that's not overfitting because I took it out, so it wasn't involved in the fitting. And that allows you, it's very intuitive. That's a nice thing about cross-validation, and the theory is tied directly to it. It says, okay, if I do this, it's one thing I can do that guarantees that I will not overfit, that I will not be creating associations that didn't exist in the data. Because if I do something that does a really great job in the training sample, but a horrible job predicting in the future, it doesn't choose it as an algorithm. It will choose something else that does a good job. So much of these algorithms we're going to talk about really rely on proofs in the pudding. They use the data as really several different experiments. They have to divide it up to do that. And that's common in machine learning in general, but also an integral part.
So we are not doing any type of cross-validation?
We are going to be.
Okay.
Yeah, I mean, you're not going to have to program it yourself. It's built in, but these procedures use lots of cross-validation. And, you know, we're just finding theoretically, you almost can't do it enough. Like you cross-validate the cross-validation, you get even better. I mean, it's limited by the computational time and things like that, but cross-validation becomes really crucial to estimation. Skip that. This is the book we're using. Here's the more technical definition of the roadmap. You can read at your leisure, but these are sort of the elements that lead up at the end to a set of software that you have, right? So I want to give you some idea what's behind the software, some justification for why it might do a relatively good job. As I said, not everybody can understand all the justification for it, including myself, but it has a strong body of work behind it. In order to do causal inference, we'll go over in more detail tomorrow, but you have to make other non-testable assumptions. Like I can't test from the data whether there's a variable missing. There are really weird, people who are really working causal inference have come up with these really complex identifiability conditions where sometimes in some circumstances you can like build the causal model, how variables are related to each other just by the empirical relationships of the variables, but generally that's not true. There's some things that you have to pre-specify that you can't use the data to test. They're not testable. And so in addition to have the statistical model, which you can essentially test because you can see if it does it fit well, you can't do that for some of these assumptions. So for some of the things we're going to estimate beyond prediction, there will be so-called causal assumptions that are not testable. We'll talk about superlineing. We'll start tomorrow. That is, how do we, if we don't know anything about the relationship of an outcome and a bunch of predictors, how do we create an algorithm that we're guaranteed to do at least as good as the thing we have in our hands? And it turns out the best way is to try them all and choose the best one. It's very simple, and that's the principle behind the superlearner. The implementation is a little bit more complicated, but that's basically it. So we'll talk about that. There's a theory called the Oracle inequality, which tells you that if I try a bunch of things and my sample size is big enough, and I don't try too many things, and let me tell you, it's hard to try too many things if you use cross-validation. And I use, like a test data set, to choose among them, I'm going to choose, as the sample size grows, the truly best one. So it gives a optimality theorem for how to do machine learning, and super learning is the implementation of that theorem. And you'll do a lot of super learning. It's very easy to use. So it's you know, it's a lot of complicated theory behind it, and the algorithm is complicated, but the implementation is not. And then we'll talk a little bit about, we'll talk a lot about how to convert those estimates into being meaningful. And I'm not going to go over this now. Yeah, I'm just going to stop here because the rest of it we're going to go over in some detail.